Hey everyone, welcome back. In our first video of this SHM sequence, we learned the definition of simple harmonic motion, a couple of definitions, period and frequency, and we looked at the first type of object that we're going to spend time analyzing in this scenario, this back and forth oscillating motion. Last video was looking at the pendulum. In this video, we're going to look at the other scenario, which are masses attached to springs, so spring objects moving back and forth, okay? There is a different equation, and there is a little tricky, weird bit going back to energy actually towards the end of this video, but you'll see that a lot of the same ideas and a very similar looking equation is going to show back up in this video. Okay, so the first thing I want to do is just a little bit of review because, again, we're dealing with objects attached to springs. So let's make sure we remember the basic physics from springs from our past sequence of videos, okay? When we're talking about objects attached to springs, we're dealing with ideal springs. An ideal spring is one where, even though it seems kind of funny, it has no mass. We're not actually we're not including the inertia of the actual spring itself, all right? So we're going to ignore its own mass. Okay? It's also one that we say obeys Hooke's law. And that's just a way of saying it's an equation, or it's a spring that follows this relationship. There's a force that the spring applies, and it's based on how much that spring, do you remember what this is? That's the displacement, how much the spring is compressed or how much it is stretched, and also based on this thing called K, all right? This spring constant, how stiff the spring is, all right? So we're going to see this equation again, and we're even going to use the same energy equation we saw before with springs, but now just looking at it in an example where an object is oscillating back and forth, or this way, back and forth, okay? Maybe something to remember about this equation, there is this minus sign classically in a lot of textbooks, a lot of physics lectures. You'll see for this spring force equation, they'll have this negative sign. I believe the AP equation sheet keeps it in an absolute value. Oops, that should be a little FS right there. They have an absolute value, which I actually appreciate, because that little minus sign tends to confuse students. It's there not because it's always acting in the negative direction. Remember, that's how we normally looked at vectors, all right, the direction. It's just because that the force is opposite the displacement. But that was really often just confusing more than anything else. So remember, if we're looking at the force from a spring, here's an example. We've seen this before already. A mass attached to a spring. If we were looking at the sum of the forces directly above me, yeah, even though the spring is acting upwards, I wouldn't plug in a negative sign because classically we would say that up is positive. And so this was our kind of callback from our prior videos, okay? So I know there's a negative sign in here. You might see that, but it doesn't change how we approach a problem. Okay, that's all just review. How do we see masses attached to springs in oscillating in simple harmonic motion? Well, I mean, to be honest, probably just like you could imagine. Let's assume that I have this mass and I've attached it to the spring, and then I take that mass, I grab it with my hand, and I pull it back some amount. How much we pull that mass back from, remember this thing called the rest position? That's that natural length of the spring all by itself without anything attached, the rest position. How much I pull that mass back is often referred to as the amplitude. And that was a word we saw similar for pendulums. Okay, that amplitude, that maximum displacement, that's how much we pull an object back. And then when I let it go, that mass is going to be moving left and then right, and then back and then forth, and then back and then forth. If there's no friction, this motion will continue. It will repeat. Oh, there we go. There's that oscillating motion. There's simple harmonic motion. Okay? For pendulums, it was the force of gravity that was the restoring force. Here it is that spring force equation. All right? And remember, it's acting backwards and forwards and flipping based on whether that spring is being stretched. When it's stretched, the force is this way. So the mass is accelerating this way. But when the spring is compressed, oh, now the force is this way. That's why it's now accelerating in the opposite direction. And that repeats, hence our simple harmonic motion. So what's causing masses on springs to move back and forth, back and forth? Well, it's the spring force, one that we already learned. Also, remember, even if you're dealing with a problem that's having to do with simple harmonic motion, you can still use and you could still apply, depending on the problem, that spring potential energy. Don't forget about that one, 1/2 kx squared. So that could still be applied. Just like when we were looking at pendulums, you could still use conservation of energy based on the height of the pendulum, the speed of the pendulum. So it doesn't mean you can't use these other things. They're still perfectly valid. okay? Now, what's being added to this? All right, we're not just looking at springs again. There's a new equation. When we have a mass attached to a spring and it's oscillating, it's in simple harmonic motion, there is a equation for the period of that spring. And here it is. This is straight from the AP equation sheet itself. T for period, remember that's the time for one cycle. And for a mass on a spring, what would one cycle be? It's this picture. It's there and back again, just like a pendulum. But now I'm starting totally stretched, for example, and then down so it's compressed, and then back so it's stretched. This is one period right here. And the time for one period, it's an equation that looks kind of similar to what we saw before. 2 times pi, those are of course constants. M, that's the mass that's attached. And K, that's the spring stiffness, Okay, that spring constant, it's often described as that also. I have a really quick animation that I can show you right here. All right, I'm going to go ahead and hit play just a moment. Here it is moving back and forth. Oh, I can drag it myself. Aha! Now, it's changing colors. That green is when the force is to the left, and it turns red, indicating when that force is to the right. But man, I mean, pretty basic, right? We have this oscillating motion, simple harmonic motion, back and forth and back and forth. The time it takes for this mass to go from here to here, that's one period. All right, that's governed by this equation that we see, okay? So especially horizontal springs, oh, pretty basic, okay? Now you just have one more tool in your tool chest, one more equation in your arsenal. You could find the time it takes that mass to go back and forth, okay? The only other thing I want to spend time on is imagine still have a spring, still have a mass. I'm still dealing with oscillating motion, up and down, but now for vertical springs, okay? Now remember, let's make sure we're clear. When I have a spring all by itself, when there's nothing attached, we have this just general length. This is known as the rest position of the spring, all right? Now imagine I have a mass, and I hook it onto the spring, and at first I gently lower the mass down. This spot here, this is where the mass, it's not launching up, it's not falling back down, because I just very gently lowered it. This is where the forces are balancing, this upward spring force, Fs, the downward weight, mg. This line here is the equilibrium position, Equilibrium meaning the equal forces that are acting on it. The spring force up, mg acting down, okay? So it's weird. There's kind of a couple like rest positions. There's the rest position of the spring all by itself. That's what we normally just call rest position. But also, if I take a mass and I just very gently lower it, it will be at rest at some point. That's known as the equilibrium position, okay? But now, I've taken my hand, I've grabbed that mass, and now I've displaced it. There's the word amplitude again, maybe uppercase A for short, amplitude. I've displaced this mass some amplitude and I let it go. What do you think the mass is going to do? It's going to oscillate up and down, back and forth. Same thing. The same simple harmonic motion. And if you're worried, oh no, we have to learn a new equation for vertical springs. Nope, you don't. It's still going to be 2 pi times the square root of m over k. I have, again, a little simulation I can show you right here. Okay? Now, here I have the masses at their equilibrium position. Now, I could show you, for example, if I take off this mass, bonk, there's the spring's rest position. But here I'm going to attach it and let it slowly and let it lower it gently to its equilibrium position. So a little different. But then I can stretch this one down and up and down. So I know my head is kind of right above this website. It might be a little weird to see me. Now, it says in the equation that we just went over that it's based on the mass of the spring. So let's look. Now, these two springs are identical. That's how I've set it up. But notice, I have a more rapid, a smaller period for the smaller mass. It takes more time, a longer period for the bigger mass, okay? Now, there's one other thing that I want to mention, actually, and this is a little weird. This is maybe the most confusing part. Remember, we can still use energy. That hasn't gone away, all right? And for a mass that's oscillating up and down, I can still use this spring potential energy, 1/2 kx squared. But here's something that's a little different. When I have a mass oscillating up and down, all of its potential energy, U total. Well, I can use that as 1/2 kx squared when I'm measuring, I'm going to say this carefully, when I'm measuring x from the, that's a terrible color. When I'm measuring x from the equilibrium position, If I'm counting this as my 0 spot, right here is where I'm saying x equals 0. Well, what would I plug in at this location? I would plug in x equals a. So what would be the potential energy of this mass right here? It would be 1/2 k a squared. What would the potential energy be right here? It would be 0. And that's where it would have all kinetic energy. And again, the spring energy right here would be 1/2 k a squared because it's the same amplitude. Now that's a little different. And to be honest, if you're thinking to yourself, wait a minute, Mr. Thrasher, wait a minute. Surely this mass is gaining potential energy. How come this U total, you're not talking about the potential energy? This is the weird thing. If you use the equilibrium position as where you are measuring the stretchiness of the spring, if you use this equilibrium position, it takes into account the gravitational potential energy. This is the weird part. This is why I'm spending time specifically on vertical springs. You might see on the AP exam a vertical spring set up like this. And I don't know, maybe you have to calculate the energy of the mass when it's right here. Don't get bogged down, if you can remember this tip, if at all possible. Don't get bogged down wrapping your head around, okay, what's the potential energy? What's the spring energy? You can actually just use 1/2 kx squared if you're measuring x from this equilibrium spot. Now that's a little weird. That is not intuitive. One way to maybe help you think about it, what was causing the spring to stretch right here in the first place? Well, it was gravity. So this spring stretching, this potential energy, well, it's happening because of that energy from gravity itself. That's not really a physics proof, but that's maybe a way to help you reason out why. Now, right here, I'm just going to delete this so you have it. I would write this down in your notes because this is an important thing, and to be honest, an important thing to review because I often see this appear, maybe one time, not often, but one time appear on the AP exam. Okay? 4 masses attached to vertical springs, whether it's oscillating or not. The potential energy of the object can be found just by calculating the spring energy from the hanging mass relative to the equilibrium position, okay? Relative to the equilibrium position. Now, if you don't like that, or you're thinking, Thrasher, why? Why would I just take your word for it? Okay, very good question, very reasonable. Khan Academy has a great video where they're proving this fact. It's not, again, super intuitive. It's actually a math proof. Here I've taken a snapshot from Khan Academy, but I have their whole video in the link in the description section. If you look at this, if you care, and you're like, oh, this is kind of interesting. This is not easy to understand as a stagnant image, but click on the link in the video. You don't have to know this for the AP class. You don't have to know this derivation. But it shows you why you could use conservation of energy, and it turns out you actually only have to look at kinetic energy and the spring potential measured from the equilibrium. So follow the link in the description if you care. It's not super important, but it is a little nuance that can help solving some of these problems a little easier. But otherwise, to be honest, this is really the focus of this video. There's an equation for the period of a mass attached to a spring if it's moving as a simple harmonic oscillator. All right? That's it. I'm signing off. Take care. Thanks for watching.